So in this video, we're going to restrict the domain of a quadratic function and use its vertex form to find an inverse. So here's the idea. Up here I have a quadratic function. And what we learned earlier was that for a function to have an inverse, or to be invertible, that it needs to be a one-to-one function. And one way to identify whether a function is one-to-one is from its graph, and asking the question, does the graph of the function I have pass the horizontal line test? And we discovered that quadratic functions or parabolas don't pass the horizontal line test, so they aren't invertible. They do not have a inverse or an inverse. So the idea is that just because the function doesn't have an inverse doesn't mean that we can't come up with ways to find an inverse over domains that are useful to us. So the idea is, for example, if I look at the vertex of f of x, which is right here, and we can see visually from the graph that it's located at -2, -5. If we were to throw away everything to the right of the line of symmetry, the line of symmetry is that line x equals -2. If we were to throw away all of the graph that is to the right of that line of symmetry and just say, I choose not to use you, and we worked with only the part of the graph that's to the left of that line of symmetry, well, this part of the graph by itself does pass the horizontal line test. So it ought to have an inverse, or in fact it does have an inverse. Similarly, well, before I move on, so I could restrict the inverse. I could use the vertex actually to easily find a way to restrict the inverse. I could say, hey, let's only use x's if they go from -infinity all the way up to the x coordinate of the parabola. So for all x on this interval, I have an invertible function that passes the horizontal line test. I could just as easily say, instead of throwing away the stuff to the right of the line of symmetry, let's throw away the stuff that is to the left of that line of symmetry. So throw away this half of the graph, everything to the left. If we threw that away, and we restricted the domain, and we said, hey, let's start with x's at -2, and let's let x run all the way to infinity if we wish. Well, if we throw away this part of the graph, we do have a graph that is one-to-one and hence invertible. So this is the idea. The idea is that we can always find the vertex and then throw away everything to the left or to the right of the line of symmetry and find the inverse function. And the way that we find the inverse function is we put the function f of x into vertex form, which then lets us use the square root property to find the inverse very easily. So for this function, we'll go ahead and tackle him on this next slide. So here's our function, f of x equals 2x squared plus 8x plus 3. We're going to put it into vertex form. We're going to use vertex form to find the vertex, which we already know from the picture was located at -2, -5. And then we're going to restrict the domain and find an inverse for f over the restricted domain. So first we put it into vertex form. So f of x equals, we have 2x squared plus 8x plus 3. So vertex form, we did that in previous videos by isolating the terms that contain x's, so the x squared term and the x term, by realizing that we're going to complete the square on those terms. And to complete the square, we know that we need a leading coefficient of 1 on the x squared. So we're going to factor the 2 off of the x squared and off of the 8x. So that's going to leave us x squared plus 4x's. And then we're going to leave this guy alone on the outside. We'll then complete the square on the terms that are inside the parentheses, so the x squared plus 4x. And we complete the square by grabbing the linear coefficient 4, dividing it by 2, and then squaring it. So we're going to have 2 squared, which is 4. We're going to add that 4. Inside the parentheses, we're going to add the 4 to the x terms. to complete the square. This is what completes the square. We then have to ask, well, how did we change the function? Well, we changed the function by adding 8 to it, because if I distribute this 2 in, I'll get 2 times 4 is 8. I just added 8 to the function, so I want to balance that by subtracting 8 from the function, because 8 minus 8 is 0. So by adding 8 and then subtracting 8, I've done no change to the function other than its appearance, equals 2 times, I completed the square on something. Whose square did I complete? I added 2 to complete that square. And then over here I have plus 3 minus 8 is minus 5. And from this I can see that the original vertex, which was located at 0, 0, remember the toolbox function is x squared, and its vertex is at 0, 0. And I can see from this that the function's been moved 2 units to the left, because I have plus 2 on the input variable, and then down 5 units. So this origin, which was the vertex of x squared, has been transformed over to -2, -5. Once I see this, I can choose to restrict the domain using the vertex. I can say, hey, my line of symmetry for the parabola or quadratic function is the line x equals -2. So we can restrict the domain one of 2 ways. We can say, hey, I'm either going to restrict the domain by letting x be an element from -infinity all the way to -2, the x coordinate of the vertex. So these are restrict the domain. And the other way we could restrict the domain is we could say, hey, instead of restricting it like that, I'm going to do x is an element of the interval from -2 to infinity. Once I have restricted my domain, I can find an inverse function for each of these restricted domains. And so what we're going to do is use the vertex form, and we're going to solve the vertex form for x. Remember, when we want to find an inverse, we solve for the input variable. The input becomes the output, and the output variable becomes the new input variable. So fortunately, if we're in vertex form, it's easy to solve for x. We want to isolate the parentheses that contains the x. So first I'm going to add 5 to both sides. So I'm going to get f plus 5 equals 2 times x plus 2 quantity squared. And then we're going to divide both sides by 2. Divide by 2. 2 divided by 2 is 1. So now the x plus 2 squared has been isolated. So I have f plus 5 all over 2. And then we'll take the square root of both sides. And when we take the square root of both sides, we get a plus or minus. And that's going to leave us with, on this line, that's going to leave us with an x plus 2, because the square root cancels the squaring. And we have a plus or minus the square root of f plus 5 all over 2. And to finish this out, we'll subtract 2 from both sides. So I'm going to get a subtraction of 2 plus or minus the square root of f plus 5 over 2 equals x, isolated on the right-hand side. So we can see here that we have 2 functions. So the plus function, remember we had a parabola that looked like this with the line of symmetry at x equals -2. The plus the square root is going to correspond to the stuff to the right of the line of symmetry, and the minus square root is going to correspond to the stuff on the left-hand side of the line of symmetry. So I have 2 functions sitting here because of the plus or minus. For the restricted domain from -infinity up to -2, which is everything to the left of the line of symmetry, our inverse function is going to be x equals the -2 minus the square root of f plus 5 all over 2. And on the restricted domain from -2 to infinity, that corresponds with everything to the right of the line of symmetry. We get the function, the inverse function, as x equals the -2, but it's going to be plus the square root of f plus 5 all over 2. So we get 2 inverse functions because of the plus or minus. One corresponds to the part of the graph that is to the left of the line of symmetry. The plus the square root, or the positive square root, corresponds to the stuff that's to the right of the line of symmetry. Okay, so what we're going to do is one more example, but this time we're going to apply this to a word problem. So this is an application. So example, suppose that a ball is thrown straight towards the ground with an initial velocity of 32 feet per second from a height of 80 feet. Find the height model, the domain of the height model, and the inverse function for the height model. So first of all, we need to remember how our height models are constructed. So our quadratic models for height as a function of time are equal to 1/2 acceleration times time squared, plus v naught, the initial velocity, times time, plus h naught, the initial height. And I see that I'm measuring in feet per second, feet above the ground. So that tells me that my acceleration in my height model needs to be in English standard measurement. So it's going to be a feet per second squared. And as discussed in a previous video, acceleration near the Earth's surface in feet per second squared is 32. And we put a negative on it because we denote downwards as negative and gravity's pulling us down. So negative 32 feet per second squared. Our initial velocity is indicated to be 32 feet per second toward the ground. So v naught is going to be negative 32 because the ball is thrown down, and this is going to be feet per second. And h naught, the initial height, is given to us as 80 feet. So we just load the equation up, the height model. So height is equal to 1/2 of negative 32 is going to be negative 16. Negative 32 divided by 2 is negative 16 t squared. And then we replace v naught with negative 32. So minus 32 times t plus the initial height was a positive 80 feet. So there's the height model. And what we want to do is restrict the domain on this height model. And this time we're going to do it graphically. So the quadratic function that we have here, I've graphed it on the interval from negative infinity to infinity. Here's what the graph of it looks like. The issue is that there are parts of this graph that don't make any sense in the context of the model. So any time that occurs before t equals 0 doesn't make sense. Those are negative times. So on the time axis, here's our time axis, every number here that's negative doesn't make sense in the context of the problem. So we want to throw away this half of the graph as nonsensical given the model. And then the ball is going to get thrown towards the ground. So when it's at a height of 0 feet, it means it's on the ground. So this intercept right here is when the ball is on the ground, and the ball is on the ground at 1.45 seconds into its flight. It's not going to go underground. So here where we have negative values for height, this part of the graph makes no sense. So the only part of the graph that makes sense is from time equals 0 to time equal 1.45. In other words, from when the ball was thrown to when the ball hit the ground. So we're going to restrict the domain. Restrict the domain. Or there's a sense in which we're not even restricting it. We're just saying, hey, the model has a domain. Time only makes sense when it is running on the interval from 0, when the ball is thrown, to 1.45 seconds after it's thrown when it hits the ground. There's my restricted domain. And I can see that this part of the graph over that restricted domain clearly passes the horizontal line test. It is to the right of the line of symmetry of the graph. So it would correspond to that positive square root stuff. So I'm going to go ahead and put my model into vertex form. And then I'm going to use the vertex form of the model to find an inverse function. So to put it into vertex form, we're going to take our height equals, we're going to take our quadratic function right here, But we know that we need to complete the square on the input variables, the t squared and t terms. So we need a leading coefficient of 1 on t squared, so we're going to factor the negative 16 off of both the t squared term and the t term. So that's going to leave me with a t squared here, and this minus is going to become a plus, and negative 16 pulled out of a negative 32 is going to leave a 2t. And I'm going to leave some space and put my plus 80 right here. And we can verify by distribution that we've done this correctly. Negative 16 times t squared is negative 16t squared. Negative 16 times positive 2 is negative 32t, so we get back what we started with. So to complete the square, we look at the stuff inside here. We say grab the coefficient on the linear term, which is 2. Have it, divide it by 2, and then square it. So we're going to be squaring a 1, which is just 1. So add 1 to the stuff on the inside of the parentheses. How much did I really add? Well, I really added negative 16 times 1 is negative 16. I really just subtracted 16. So I'm going to go plus, I'm going to add 16 to counteract the 16 that I just subtracted. So now I can continue to complete the square. Negative 16. I completed someone's square. Whose square did I complete? I did t, and I squared a 1, so it's going to be plus 1. Plus 80 plus 16 is 96. And there I have completed the square. I can actually identify from this vertex form the location of the vertex. The vertex is located at, well, the origin on the toolbox function was shifted over 1 to the left and up 96, so this should be located at negative 196. Not necessary for us to locate the vertex. We're not being asked to do that. We really just need this restricted domain. So let's go ahead and find our inverse function over this restricted domain. So to do that, we need to solve for time. So to solve for time, my first step is to subtract 96 from both sides. So I'm going to get height minus 96 equals negative 16 times t plus 1 quantity squared. We're then going to divide both sides by negative 16. Divide by negative 16 equals negative 16 divided by negative 16 is 1. That's going to leave us with 1 t plus 1 quantity squared. I'm going to take the minus sign here, and because the minus sign doesn't care if he's in the numerator or denominator, I'm actually going to move him up into the numerator position, and then from there distribute him into the parentheses. So I'm going to get a minus h and a plus 96. So I'm going to rewrite my numerator as 96 minus h by distributing the minus that was originally on the 16 into the numerator. It's going to be over 16. I don't need to do that. I think it makes things look cleaner. And then I'm going to get rid of the squaring here to try to dig the t out. So I'm going to take the square root of this side. I'm going to take the square root of this side as well. And usually you would do plus or minus. But here I've restricted the domain so that I'm only after the part of the graph that is to the right of the line of symmetry. So I don't need the minus or negative square root. I just need the positive square root. So on the next line down, I see that I get a t plus 1, and it's going to be the square root of 96 minus h all over the 16. And then we subtract this 1 from both sides to finish up. So when we subtract it from both sides, we're going to get a square root of 96 minus h all over 16. And it's not going to let me write down there because it's bringing up tools. So I'm going to have to kind of sneak up into here to finish this. So that's going to be a little bit unfortunate. So I'm going to subtract the 1 from both sides. I'm going to get the square root of 96 minus h all over 16 minus the 1 is equal to t. And this is the inverse function. It allows you to plug heights in and figure out the time at which you were at that height. And in fact, what we can identify is that our heights, we can figure out, ooh, what's the domain of the inverse function? Well, to answer that question is, where do the heights run from? Well, the height, the lowest you can get is 0 when you're on the ground. And the highest we get in the model is 80, which is the height from which the ball was initially thrown. So this inverse function, as long as we plug in heights between 0 and 80, we'll get output times that are between 0 and 1.45.